Okay, so this is our second part of 4.8, and we're talking about simple harmonic motion. Now, a point moving on a number line is in simple harmonic motion if its directed distance d from the origin is given by either one of these equations. Okay, so if it's given by either one, and it's going back and forth on a number line, and we're talking about harmonic motion when it's going back and forth like this. Okay, so it's a sinusoidal wave. Okay, now keep in mind as we're doing this, where a and omega are real numbers and w, omega, is greater than 0, the motion has frequency, omega 2 pi, which is the number of oscillations per unit of time. Now, as we're going through the frequency and period, notice that the harmonic motion is sinusoidal with amplitude, absolute value of a, and the period is 2 pi omega. The frequency is the reciprocal of the period. So keep in mind those things as I'm doing this. Now, in a mechanical linkage, let's talk about it like this. In mechanical linkage like the one shown in figure 4.94, right there, a wheel with an 8 centimeter radius turns with an angular velocity of 8 pi radians per second. Okay, so let's talk about a few things that I have. This 8 pi radians per second is omega. Okay, and if I'm looking at this, I'm talking about my radius, which equals a, which also it happens to be 8 here. And then I have my omega. Okay, now the piston makes 4 back and forth motions per second. And if I wanted to find my frequency, which is omega over 2 pi, I take my 8 pi, which is omega, divide it by 2 pi, and that's my 4, and that's how often that's where I got this, okay? That's where I've got that. Now let's talk about our model itself, because I've given all the information in there, and because of the picture I have in my graph, and you guys have this same picture, because of the picture I have in my graph, I'm thinking that, you know, I really need to look at it, and I'm going to use cosine. And the reason why I'm going to use cosine is starting up here. So for my model, okay, d is equal to a cosine omega t. Okay, well, d is equal to a was 8, cosine omega was 8 pi, and I have x instead of t, and really that d should be our y. Okay, so we're gonna fix that up right away. We were adjusting our model to fit our graph as we need. So y is equal to 8 cosine 8 omega x. Okay, and perhaps I should have done that when I did this setup. Now, what's the distance from the starting position? So I'm going to look at this, and this is, again, my y, okay? And I'm going to pop that through at 0, and we have our distance, d, which is y, and this is our original starting position, 8 centimeters. Now, remember, that's 8 centimeters up here. Okay, that should be 8. Now, as we're going through, they're asking at 3.45 seconds. Okay, at 3.45 seconds as we go through. Now, I've got this still, this is y. This is my model. 3.45 is going to go in there because I'm wondering how far that distance is at 3.45 seconds. Okay, and remember, every second it cycles 4 times. Okay, every second this cycles 4 times. So this is our position 3.45 seconds after starting. So although it's been 3.45 seconds, there's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then 0.45, 1, 2. We're right here on our graph because this is about 3.45 seconds. And this is where we're at this point at 3.45, that is my x, and my y is 2.472. Okay, so I want you to keep that in mind as we're going. That's where it is. My graphing calculator information is right there. I put it in y1 and y2 so I could check it out. And I got this information here. That's where I got that. That is my original function that I'm plugging in. And these are my values at 3.45. Now, that's my position, but you got to keep in mind my starting position was 8 centimeters. And right now I'm at 3.45, and the question is, what is the distance from the starting position exactly 3.45 seconds after starting? So I'm asking really is, I'm going to pull this up, I've got that little dot. How far away is this distance? What's this distance? So as I do it, my starting distance as I go through, the distance from the starting position is 8 minus 2.472 is 5.528. So I am 5.528 centimeters from the starting position. 3.45 seconds after the start. Okay, and that's the end of my answer there. So let's go on to our next problem. A mass oscillating up and down on the bottom of a spring. Okay, we're going to make an assume a perfect elasticity and no friction or air resistance. So that those things won't be problems for us. Okay, now can be modeled as a harmonic motion if the weight is displaced a maximum of 5 centimeters. Find the modeling equation if it takes 2 seconds to complete one cycle. Now, when I'm starting this, I have a choice as I'm going for my model. I have d equals a sine omega t, or d equals a cosine omega t. Okay, now I've got to make a decision on which one I start at, and you've got to be thinking, I've got a choice. If it's going to start way at the bottom, okay, I can start with cosine. If it starts way at top, I can use cosine. But this neutrally is in the middle. So I'm going to use sine here because the sine starts on the axis. So that's why I'm going to use the sine value. Now I'm going to reread to find the other thing. So we're going to use sine because of where it starts. Okay. Now a mass oscillates up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, can be modeled as a harmonic motion. If the weight is displaced a maximum of 5 centimeters, this maximum of 5 centimeters, this is my A. That's my amplitude. Okay. Find the modeling equation if it takes 2 seconds to complete one cycle. Well, fine. If the modeling equation, if it takes 2 seconds to complete one cycle. So if I have 2 seconds to complete one cycle as I'm going through here, and it's one cycle, one period is 2 seconds, so the inverse of that period. So let's talk about this. I've got A is equal to 5. I've got 2 seconds per cycle. My period is 2, and my frequency, that makes my frequency, because period and frequency are reciprocals of each other, 1/2. So frequency is 1/2, period is 2. Well, I've got an equation here that says F is equal to omega 2 pi, and I already know that that's 1/2. So I'm going to multiply by 2. And remember, what I'm solving here is W 2 pi equal 1/2. I'm solving that. So W is equal to 1/2 times 2 pi. So W is equal to pi. So I got omega, and I have A. So I can write my model. So my model should be D is equal to 5 sine of pi t. But if I put it in my calculator, in my GC, if I'm going to use it, it's going to be y equal 5 sine of pi x. And I should make it actually a sine versus a psi. So let's make it sine of pi x. So that is my modeling equation. And that's what I was asked to find. Okay? So however you want to look at it, my modeling equation there or there, based on whether I put it in the graphing calculator or I just have it out my answer. Now, the chapter opener problem, solutions on the bottom. I'm just going to let you read it, and that's going to be it for today's second part of notes, and that's our section. 4-8, page 393 to 396, 1, 2, 3, 5, 6, 7, 10, 15, 16, 17, 18, 19, 22, 27, 29, 31. I will be back on Monday and we'll discuss any issues that you had with this assignment. Hopefully things go extremely well and we'll be able to check in with each other in a positive note. Now, remember, we have a test next week, and because I'm gone and because of a half day, it's going to be Thursday instead of Wednesday. So Thursday, the 9th, we will have our test on part A of part B of 4.7, and we will start 5.1 on Friday. Hope you guys have a great weekend. Talk to you soon. Bye.